So last time we have learned the reversible and irreversible process. So okay, this is another classification. This is another classification of thermodynamic process. Isothermal, isobaric, isochoric, adiabatic, polytropic. In isothermal process, the temperature remains constant. Isobaric process pressure remains constant. Isochoric process volume remains constant. Adiabatic process heat transfer is zero. Polytropic process is a reversible process. Okay. The equation for polytropic process is PV power n is equal to constant. Okay. So these are different types of thermodynamic process. Isothermal, isobaric, isochoric, adiabatic, and polytropic. Okay, note it down. Note it and raise your hand quickly. Okay. Raise your hand if noted. If noted, you raise your hand, please. Okay. Now coming to first law of thermodynamics applied to various processes. First, so we can study the first isothermal process. So isothermal process, the first law you can apply, heat transfer equals to work done plus change in internal energy. Heat transfer equal to work done plus change in internal energy. Heat transfer in the process 1 to 2. Work done in the process 1 to 2. Change in internal energy. Heat transfer, work done, final internal energy minus initial internal energy. Okay. Change in internal energy depends for ideal gas. The change in internal energy is mainly dependent on, in anyway, macroscopic internal energy is zero only. So it's only microscopic, and change in internal energy is only function of temperature for ideal gases. For ideal gas. Okay, so function of temperature is constant in this process. So change in internal energy will be zero. Whatever heat you are transferring, that is directly getting converted to work. Okay. Heat transfer equal to work. Okay, there is no change in internal energy in isothermal process. This is the first law applied with the isothermal process. Okay. For ideal gas. Okay. Noted. Noted na, raise your hand. Okay. Okay. Noted. Now I will tell you about Nishant. Noted. Now coming to ideal gas equation. First of all, you should know what is ideal gas. Ideal gas means it's a imaginary one. Okay. first of all. Second, the intermolecular forces is zero. Okay, this is the main assumptions in ideal gas. Okay, intermolecular forces are zero, and it's an imaginary gas. Okay, now this ideal gas, there is one equation called ideal gas equation. The ideal gas equation is, this is the ideal gas equation, famous ideal gas equation. P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin. Okay, PV equals to nRT is the ideal gas equation. Can you note it down, this one, and raise your hand after completing? This ideal gas equation is nothing but, suppose there is a gas contained in a inside a container. So whatever the volume of the container, it will occupy that volume of the container, right? That is the volume. Pressure means what is the force with which the gas is striking the container, like that, something like that. That is the pressure of the gas. Temperature is the temperature of the gas. So N is the number of the moles of the gas inside the container, and R is the universal gas constant. So the pressure, volume, and temperature of the gas are interrelated. They are not independent, but they are interrelated with each other. PV is equal to nRT. Very famous equation. Okay, there's the ideal gas equation. That's called as ideal gas equation. PV is equal to nRT. Very famous. Okay. Now, if you apply the ideal gas equation in the first law of thermodynamics, sorry, if you apply the ideal gas equation in isothermal process, so isothermal process is PV is equal to nRT. So temperature is constant. N is also constant generally. R is also constant. All these things are constant in a closed system. That means multiplication of P into V is a constant. PV is equals to constant. That means if you are going from state 1 to state 2, then P1 V1 will be equal to P2 V2. This is the equation for isothermal process. PV equal to constant represents isothermal process. Can you note it down? And it is a reversible process only. Anyway, it's a I'll explain you further why it is like that. It's a reversible process we are talking. Okay. So P1 V1 equal to P2 V2. Note it down. Note it down. Okay. Like this, in every process, you have to apply the ideal gas equation. Second process we are studying is, so one more thing we want to calculate is the work done. Work done in isothermal process. Work done in isothermal process. Now actually the work done which we are talking about is PDV work. Pressure into volume. Pressure into change in volume, slight change in volume. That is work done is equals to integration of P into dV. How this comes into picture, I will explain you. Suppose you are having some gas which is expanding. So there will be change in the distance, this delta x, into area, and some pressure is being applied, right? So pressure into area, that is force. Force into displacement is work. A into delta x is delta V, change in volume, P dV. Small dV because pressure may change, right? So with for the small time the pressure remains constant. So P dV and summation of all that small P dV from one point to another point. So from V1 to V2. Integration of P dV. That is the total work done from 1 to 2. This is called, this is a standard equation for any reversible work. For any reversible work, this is a standard equation. Integration of P dV. Okay. This is not work done in isothermal process. This is a normal work done everywhere. You can use this, apply it anywhere. For a reversible process, work done is equal to integration of P dV. Okay. This you note down and raise your hand. Then we will derive the equation for isothermal process. Noted? Noted, Nishant? Now we will derive the work done for isothermal process. Again, the formula is same only. Now we know that in isothermal process, pressure into volume is constant. So pressure can be expressed in terms of volume, like this. C will come out. 1 by V is log V, you know, formula. V1 to V2. Log V2 minus log V1. Till this you note down, then I will further solve it. Note down till this and raise your hand. Noted now. So this derivation again I will repeat it for you so that you can just get an idea how to do it, and then finally we'll get the formula. Work done is equal to This is the standard formula that log A minus log B is log of A upon B. This C is nothing but PV only. So you can write C as P1 V1 or P2 V2, anything you can write it. This is the formula, final formula. Instead of this, you can even write P2 V2 also. Note it down. This is formula for isothermal process. Clear? Note it down, please. Note it and raise your hand. Note it and raise your hand. Now we'll derive the work done formula for various for process. One by one, we'll apply the study the various process. This process is over. And one more thing I would like to tell you, final highlights about isothermal process. Temperature is constant. PV is equals to constant. Work done is P1 V1 or P2 V2 log of V2 by V1. Heat transfer equals to work done. Therefore, heat transfer also formula is same only. Right. These are the final highlights for isothermal process. If you draw the graph between pressure and volume, it will look like this. I will show you. That also you can write, note it down. This is the graph for pressure volume. It's like a rectangular hyperbola. It's called a rectangular hyperbola. Note it down all the 6 highlights about isothermal process. 6 highlights about isothermal process. Note it down. Note and raise your hand. Okay. Now, noted now. Now we'll go to isochoric process. Or let us do adiabatic process first. Adiabatic process. The main highlight of this process is that the heat transfer is zero in this process. That means the process is done in such a manner. Now, what is the meant by process? See, process means nothing but heat and work transfer to a system. Maybe the system means the gas, which is enclosed in a certain container in a certain arrangement. The gas may be enclosed inside a container. We are talking about closed system only. All these formulas are applicable for a closed system only now. So some gas will be confined in some container, but the heat transfer is not allowed, means it's insulated from the surrounding. So this is one kind of adiabatic process. Okay. Now it's not allowed to exchange the heat with the surroundings. Only work transfer is allowed with the surrounding. Okay. That kind of process is called adiabatic process. So heat transfer is zero. If you apply the first law, which says that Q is equal to W plus change in internal energy, right? So Q1 to 2 is zero, right? So work done, whatever the work done is equal to minus of change in internal energy. That means the work is done at the expense of internal energy. That means internal energy will reduce. Okay, if the work is done by the system, that means if it is an expansion process, work is done by the system, right? Expansion process. If expansion process, internal energy will reduce, will decrease. Work is done at the expense of internal energy. You can write it down. Work is done at the expense of internal energy. Work is done. Okay, system may expand, but the energy will reduce. That means temperature will go down because internal energy is a function of temperature for ideal gas. So if that means expansion process, cooling will happen. If there is expansion in adiabatic expansion process, that means heat transfer is zero. Automatically, the whatever the substance will get cooled down, and with that energy only it is getting expanded. Okay, with the help of internal energy. Okay, heat transfer is zero. No heat exchange with the surroundings. With its own internal energy, it's expanding and it's getting cooled down. Okay. So this is first thing you note it down and raise your hand. If it is clear to you, you note it down. Adiabatic process. Heat transfer is zero in adiabatic process. That is the main thing in adiabatic process. Note it down, please. Note it down. Noted. Mahalakshmi noted. Work is done at the expense of internal energy. Okay. Now let us come to some more aspects about, again I will highlight it, that heat transfer in adiabatic process is zero. So the first law when you apply on the adiabatic process, then you understand that heat transfer is zero. So work is done at the expense of internal energy. This is the equation followed, which is doing the adiabatic process. This is the adiabatic process equation. P1 V1 power gamma is equal to P2 V2 power gamma. This is the equation for reversible adiabatic process. Reversible adiabatic. I'm not doing the derivation, but I am telling you the formula directly. P1 V1 power gamma. What is gamma? Gamma is the specific heat ratio. Ratio of specific heats. Now you might have studied Cp by Cv. Specific heat at constant pressure and specific heat at constant volume. So gamma is the ratio of specific heat. Gamma is predefined for each gas. Monatomic gas, gamma is different. Diatomic gas, value of gamma is different. And triatomic gas, value of gamma is different. That we'll study in detail afterwards. Okay. But this is the process. This is the equation for reversible adiabatic process. You please note it down. Okay. Is it clear? Noted. So this is a reversible adiabatic process equation. Now we'll apply the. Now what else we can do is we can find out the work done in adiabatic process. Give the heading work done in an adiabatic process. Work done in adiabatic process. Work done, still the formula remains the same. This is for any reversible process, formula is the same, but now P we can write as C upon V power gamma, right? Because PV power gamma is equal to constant, right? So from that we can write pressure is C by V power gamma, right? Am I correct? This we can do. And dV. So what we'll do is C will come out and V power integration of V power minus gamma dV, and then what will happen is v power minus gamma plus 1 upon minus gamma plus 1, n plus 1 upon n plus 1. You know the formula, v2 to v1, sorry, v1 to v2. Okay, so note up to this one, then I will tell you next what we have to do. Note it down and raise your hand. So this is the first part, then finally we'll derive it formula. Note it down, note it down, note it down, note it and raise your hand. Noted everyone? Now I will tell you the final derivation. So work done will be, again I am doing it from the start for your understanding purpose. Gamma is the specific heat ratio, Cp by Cv. This will come out 1 minus gamma, V2 power 1 minus gamma minus V1 power 1 minus gamma. Now what is C? That also we can write. C is nothing but P into P1 V1 or P2 V2, whatever you call it. P1 V1 or P2 V2, whatever, whenever you want, we will use accordingly power gamma, right? Now what we are going to do is, whenever we are multiplying with V2 power 1 minus gamma, we will use the P2 V2 power gamma. When we multiply with V1 power 1 minus gamma, we will use P1 V1 gamma. Okay. So when the P2 V2 power gamma into V2 power, so P2 and V2 power gamma plus 1 minus gamma when they are multiplying. So P2 V2 minus P1 V1 will come. You can check at home. So this is the final answer. What is the final answer? P2 V2 minus P1 V1 upon 1 minus gamma. This is the final answer. Okay. Note it down. Okay. Final answer. Note it down. Noted. Noted everyone. Harini, noted. This is the final formula. Remember, okay? Formula is very, very important. All the formulas are very important. Separately note it down, all the formulas. Okay, now I am proceeding. Okay. So now we'll look at the various aspects of adiabatic process. Various aspects of adiabatic process. Number one, that heat transfer is various aspects for adiabatic processes. Number one, heat transfer is zero. Number two, the whatever the work heat transfer is zero, whatever the work transfer, that is E1 minus E2, that is at the expense of internal energy. Third, that expansion causes cooling. Expansion causes cooling, temperature drop. Okay, expansion causes cooling. Fourth, PV power gamma equal to constant. Fifth, work done is P2 V2 minus P1 V1 upon 1 minus gamma. These are the 5 aspects of adiabatic process. If you have noted these 5 aspects, just raise your hand. After noting it, raise your hand. Okay. Noted, everyone? Noted. Now we will go to the next type of process. We have done two processes till now, isothermal adiabatic. Now we'll see the isobaric process. Isobaric process means pressure is constant. First apply the PV equal to nRT ideal gas equation. Pressure is constant, N is constant, R is already constant. So volume directly proportional to temperature. That means V1 by V2 is equal to T1 by T2. This is the equation for isobaric process. Work done formula. Work done formula integral P dV. Pressure is constant, so P will come out. Integral dV. Integral dV means V. 1 dV means V. So the answer will be P into V2 minus V1. This is the work done formula for the isobaric process. Okay. All these things very important. Okay. In fact, okay, all these things. Okay. So this you please note down. First, pressure is constant. Second thing, ideal gas equation, how to apply and what is the result for it. This is the equation. And third thing, work transfer in isobaric process. Note it down, please. All these things. Note it down, ABC. Note it and raise your hand. Noted. Nishant, noted. Noted, Nishant. 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 Nishant, you are there in the class. So next, isobaric process, and then we come to the isochoric process. Fourth process, isochoric. Isochoric means volume is constant. So that is isochoric process. Pressure into volume. Now, if volume is constant, okay, volume is constant. First, we see understand that if volume is constant, work done will be zero, because work done is nothing but expansion or compression. Displacement is very important in work done. If there is no volume change, then work done will be zero. So isochoric process, work done is zero. Number one. No need to calculate the work, and work done is nothing but heat transfer plus change in internal energy. So work done is zero. Na heat transfer is nothing but E1 minus E2. That means whatever the heat transfer you will do, that will increase the internal energy. Whatever the heat transfer we do, that will increase the internal energy of the system. Whatever the heat transfer we are doing, that will increase the internal energy of the system. Either it will increase or decrease. If there is heat is rejected from the system, the internal energy will decrease. If heat is added to the system, internal energy will increase. Okay. Okay. And the third thing is change in internal energy, and the third thing is isochoric process, work done we have seen. That's all. Okay. So these three things, and third thing is PV equal to nRT, that N is constant, R is constant, and V is also constant now. So pressure is directly proportional to temperature. So you can say P1 by P2 equals to T1 upon T2. These are the three things you should know for isochoric process. Note it down. Volume is constant. That means volume is not at all changing. That means there is no work done. That is very important. Okay. So these are all three important formulas which are very important for isochoric process. Note it down and raise your hand, please. For isochoric process, note it down and raise your hand. Hmm. Now we'll come to the fifth type of process, which is polytropic process. Polytropic process nothing but PV power n is equals to constant, and that's all. Okay. And work done formula for this one will be P1 V1 minus P2 V2 upon n minus 1. This is a work done formula. That's all. These two things are important for polytropic process. Okay. Note it down, please. Note it down. Note it and raise your hand. Noted. Nishant. 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 Ah. Now coming to this graphical representation of all the process. First one we have seen the isothermal process. I told you it will be represented like this. Second one, this is isothermal, which is PV equal to constant. This is point number one and this is the point number two. Now, if it is a constant pressure process, it will be like this. If it's a constant volume process, this is isochoric process. Volume is constant. Okay. If it is a constant pressure process, it will be like this. Okay, this is pressure equal to constant. Okay, isobaric process. Okay, so like that, this is PV power 1 equal to constant. So I will show you one graph where all the process we can represent. Okay, another two process also we can represent. Okay, I will share with you one image so that correctly I can tell you the graphical representation of various isothermodynamic process. These are all called thermodynamic process. Okay. I think this will be helpful for you. This is for expansion, this is for compression. Note it down. N equal to 0 means PV power 0. That means P is equal to constant. Okay. N equals to infinity means PV power infinity is constant. That means what you say? That means n equals to infinity means volume is equals to n equal to infinity means, yeah, volume is equal to constant. Okay, so volume is constant, that is n equal to infinity. Okay, and n equal to 0 means pressure is constant. Okay, then n equals to 1, that means PV equal to constant, that means isothermal process. N equals to n, this is a polytropic process. Okay, polytropic process. Okay, and the next n equal to gamma means adiabatic process. So main process which you are seeing here is, this is pressure equal to constant, this is volume equal to constant, this is what you call isothermal, and then this one is polytropic, and this one is adiabatic. Okay, likewise compression process. N equals to 0 means pressure is constant, this is volume is constant, then PV isothermal, then polytropic, then adiabatic. Okay, like that. Okay, so please note down this graph. Okay, and this is talking about the slope. I will explain you this. Okay, now you just draw this diagram, then I will explain you. After noting it, please raise your hand. Noted. Helen Harini. Noted. Okay, so in your homework, one more homework. Now I'm not concluding the class. I'm just telling one homework. You can make one chart like that here. Just I'm doing in. You can make one chart like this. Here you write the process name, and what is the first law result for that process, what is the ideal gas result for that process, and what is the graph of that process, and what is the special point about that process. Okay, for example, isothermal process, first law, when you applied on the isothermal process, you got that the change in internal energy is 0, so Q is equal to W. Ideal gas equation, when you applied, you got that PV equal to constant. The graph, you can draw it, and the special point is that whatever heat is given, that is converted into work. Okay, that is the for isothermal. Like that, for all the 5 process, you draw this chart in your home, one proper sketch pen, you do it and put it in your wall. Okay, take a photo and send to me. Okay, afterwards. Like that, you have to do with a sketch pen, you write all these 5 points and all the 5 diagrams and characteristics, and always see that and try to memorize it. Okay, and also that adiabatic process, heat transfer is 0. So whatever, what is the heat transfer is 0. In fact, one more column you can write here, temperature is constant, heat transfer is 0. And if heat transfer is 0 means whatever the work done, that is a change in internal energy, then PV power gamma is equal to constant. Then the graph, and the special point is that whatever the work is done, that is done at the expense of internal energy. Third thing, pressure equals isobaric process, pressure is constant, what is the formula for work done, and also the work done formula you should write. Okay, one more column you can make work done formula for each one. Okay, so like that you can summarize all the characteristic of all the different thermodynamic process. Okay, clear. Now coming to what are the other things left in this chapter. Okay, I will see that, and then I will teach you now. Okay, so I'll check. Let me check what are the different things remaining in the chapter. Okay. First law, I think mostly we have covered everything. Now second law I have to start then. Let me check. Okay. First law we have done. Zeroth law I have to teach you. Heat, internal energy, work done we have taught you. First law of thermodynamics taught you. Work done formula I have taught you. Specific heat capacity I have to teach you. Equilibrium I have taught you. Quasi-static process I can just tell you one time. Okay, then what else? All other process I taught you. Okay. Now, what are the things left? One, heat engines. Then heat engine is there. Refrigerator and heat pump is there. Then second law is there. Kelvin Planck statement, Clausius statement, reversible irreversible process already taught you. Carnot engine is there. Derivation for Carnot engine is there. That's all. That's all here. Nothing is there then. Someday yesterday I was seeing one more thermodynamics chapter. Too many things were there in that. I don't know from where I got that one. Some other wrong chapter I was seeing. Here very limited things are there. Okay, only few things are left out. A major portion we have done. 60% we have done. 70%, 30% only left. Application wise only. Okay. So what are the things left? One by one I will tell you. Okay. One by one, whichever topics are left, I will tell you. Okay. First, I will tell you about a zeroth law of thermodynamics. Okay. Zeroth law of thermodynamics. I will teach you now. We'll take a 5-minute break. Okay. Then we'll do it. Okay. Take a 5-minute break. Then we'll join. Okay. Okay, all are there? Raise your hand. Hmm. All are there, na? Right. Okay. So we have to come start what? Hmm. First, zeroth law of thermodynamics, right? Zeroth law of thermodynamics. This is very simple. There is one object, right? There is one body with certain temperature. There is another body, another temperature. Keep them in contact with each other. Keep them in contact with each other. Okay. Keep them in contact with each other, right? Okay. Keep them in contact with each other. So what will happen if you keep them in contact with each other? The temperature will equalize. The temperature will equalize like that. And likewise, if you have another body with another temperature, whatever temperature, and again that also you keep them, both of them in contact with each other, this with the first body. So what they are telling is that if you have three bodies like that, and first you keep this body in contact with this one, and temperature will equalize, and then you keep this body in contact with this one separately, and temperature will equalize, then this, that means these two are in thermal equilibrium. If these two are in thermal equilibrium and these two are in thermal equilibrium, then these two will also be in thermal equilibrium. Like that, the zeroth law says that. Okay, that is the zeroth law of thermodynamics. That I will show you the statement. Okay, that they say that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. That's what they are telling. I'll show you the thing in your book, given in your book also. Okay, so that is all about the zeroth law. Okay, you see here, you see here. Now I think all of them are C is in thermal equilibrium with A. That means heat transfer is allowed between them. Okay, and heat transfer is allowed between A. C is in thermal equilibrium with B. So A and B also will be in thermal equilibrium with each other. That's what they're telling. Okay, here they written the explanation also. Okay, I'll explain that also. That explanation. Here you can read it. System A and B are separated by adiabatic wall. Adiabatic wall means which does not allow the heat transfer. Okay, this is adiabatic wall. They are not allowed to heat transfer with each other. They are only allowed to and connected with third system by conducting wall. So here heat transfer is allowed. Here also heat transfer is allowed. Okay. Afterwards, what they do is adiabatic wall they are replacing by a conducting wall. Now this is a conducting wall and this is adiabatic wall. Okay. That is all they are doing a time pass. Okay. But only one thing, that as I explained you, that here you can read it and you can just memorize it. The two systems which are in thermal equilibrium with the third system separately are in thermal equilibrium with each other. Okay. That is called zeroth law of thermodynamics. Okay. Okay, right. Now we can move ahead. Now I will tell you what are the remaining topics. Okay, zeroth law is over. Then I will teach you specific heat capacity. Okay, specific heat capacity. You can write this one law, this zeroth law from yourself, from by just copy it from the book, note it down. Okay, I'll give you 2 minutes to note it down. Then I will tell you the specific heat capacity. Okay. Okay, noted now. Now we'll come to the next topic, that is specific heat capacity. Okay, specific heat capacity. Specific heat capacity is nothing but if you heat any substance, okay, if you heat any substance, its temperature will increase, right? Now it depends which substance you are heating. Some substance you have to heat more, you have to supply more heat energy for the same rise in temperature. If you want the temperature to rise by 1 degree Celsius, depending on the type of the body, you may have to supply more heat or less heat. How much heat you have to supply for unit temperature rise, for unit, for 1 degree rise in temperature, how much heat you have to supply, that is called specific heat capacity of the body. That is called what? Specific heat capacity of the body. And per kg, per unit mass of the body, and per degree Celsius increase in the temperature, how much heat you have to supply for 1 kg mass of the body to increase its temperature by 1 degree Celsius, that is called specific heat capacity. Okay, is it clear what is specific heat capacity? How much heat, you can note it down, how much heat you have to supply to increase the temperature of a 1 kg body, 1 kg mass of the body by 1 degree Celsius, that is called specific heat capacity of the body. Okay, how much mass, how much heat you have to supply for increasing the temperature of 1 kg body by 1 degree Celsius is called specific heat capacity of that body. Okay, this is the thing. Okay, clear? How much heat you have to supply to increase the temperature of the body, unit mass of the body, by 1 degree Celsius. How much heat you have to supply, that is heat, how much heat you have to supply, that is only the specific heat capacity of the body. And sometimes you say only heat capacity. Heat capacity means how much heat you have to supply for unit increase in the temperature of the body for the given mass of the body, that is a heat capacity. Okay, not for 1 kg mass, for the given mass. Okay, that's all. Now it's all depends in what situation you are heating the body, whether you are heating the body at constant pressure or you are heating the body at constant volume. How you can heat something at a constant volume means you have a closed box or closed container. Constant volume means closed box or closed container. You have a gas inside it and you are heating it. That is heating at constant volume. That is the heating at constant volume. Okay. Then in that case, whatever the heat supplied for increasing the temperature by 1 degree Celsius and for unit mass, that is called specific heat at constant volume. Specific heat at constant volume. Okay, this is first thing, that when you are heating the body at a constant volume process, in a constant volume process, that is called specific heat capacity of the body at constant volume, CV. That is called CV. Okay, and this is, you can note down. Okay, what is the definition of CV? When you are heating the body at a constant volume process, and how much heat is required for increasing the temperature of the body 1 degree Celsius of 1 kg body, that is called specific heat capacity at constant volume, CV, specific heat capacity at constant volume. Okay, note it down and raise your hand. Then I will tell you specific heat capacity at constant pressure. Okay, note it and raise your hand, please. Okay. Now specific heat at constant volume means that means you are going to heat it in a container, okay, such that suppose this is the thing. Now here you can see that you are some constant pressure is acting on it, right? That is atmospheric pressure, right? Or you can heat it in open container also. That is also fine. Heating it in open container. That time also the constant pressure is only acting, right? So if but a open container, a gas will escape out. So if you don't want the gas to escape out, you have to heat in a closed container, but it's allowed to move freely out. The piston is allowed to move freely up. That means volume is not allowed, is not constant, but pressure is remains still constant, because it anyway, if there is an increase in pressure, it will move out and equalize the pressure. So inside pressure is also atmospheric and outside pressure is also atmospheric. So pressure is constant. So such type of heating when you should do the heating, such type of heating at a constant pressure, that is that type of heat, how much heat you have to supply for increasing the temperature by 1 degree Celsius of that gas, of 1 kg gas, that is called specific heat at constant pressure. Okay, note it down and tell me, raise your hand. The amount of heat to be supplied when you are heating a gas at a temperature at a constant pressure process, that is called specific heat at constant pressure, CP. Okay, CP. Note it down and raise your hand, please. Noted. Noted, everyone. Now come to the remaining topics. What are the topics remaining? I'm checking one by one. What are the topics remaining? So quasi-static process, that is one more topic which is remaining. I will tell you what is quasi-static process. See, I told you now that in case of a reversible process, I told you last time that in case of a reversible process, the states undergone by the system are reversible states, are equilibrium states, right? Remember, I told you, note it down. So when that states undergone by system are equilibrium states, now there are lakhs and lakhs of states in between, right? So you cannot ensure that each and every state is a equilibrium state, okay? So we cannot have a exact reversible process, okay? We can only have a quasi-static process. Quasi-static process is just like, it's a reversible process. It's like a reversible, it's not a reversible process, it's as good as reversible process, in which most of the states undergone by the system are reversible states. You cannot ensure each and every state because there are lakhs and crores of states, because you can do the process as slow as possible, but there is a limit to everything, right? So quasi means something which is not real. Quasi static, okay, quasi static means not exact static, but it's quasi static. Quasi static reversible process means most of the states undergone by the system in quasi-static process are equilibrium states. That's what you have to write. Most of the states, most of the states undergone by the system are equilibrium states. That type of process is called quasi-static process. It is as good as reversible process. Okay, it is a representation of reversible process. Okay, quasi-static process is a representation of reversible process. I will explain you in one manner. Okay, I'll explain you. Just note it down, then I'll explain you further. Okay, most of the states undergone by the system are equilibrium states. Okay, it is as good as reversible process. That process is called quasi-static process. Okay, note it down and raise your hand, please. And I explain you further. Okay. Noted. Noted. Everyone. Harini. Hmm. So one thing I will tell you, see, I'll give you an example of quasi-static process, very famous example, okay? What here we are doing is, these are all the weights, maybe 1 milligram weight, okay? One by one we are going to remove them. When you remove them one by one, then the what is happening initially, na? Initially I am telling you, it is in equilibrium. That means outside pressure, that is whatever the pressure plus weight, outside pressure, atmospheric pressure into area plus weight of this all these blocks, that is equal to inside pressure of the gas into area, right? Then only it can be in equilibrium. You understand that inside force is equal to outside force. Then only the thing is in equilibrium. Okay. Above that, so many weights are there, right? So all those things. So outside atmospheric pressure into area and plus the weight of all the blocks, that is equal to the gas pressure into area, that both are equal. Now what happens when you remove one of the weights? When you remove one of the weights, the outside pressure is lesser as compared to inside pressure. Very, very less. Very, very minute difference. Okay. Because of that minute difference, the block will move further. There is a change in volume. This piston will move further up. There will be a small change in volume, increase in volume, and piston will move further up until the pressure inside the pressure of the gas will reduce and will become equal to the outside force, whatever is that. Okay. So in this way, we are increasing the volume by a marginal and decreasing the pressure. Okay, this is a kind of quasi-static process because we are doing the process so slowly that it is still in equilibrium. So again, the new state which has come is in equilibrium state. Previous state was also in equilibrium state, but while it is moving, at that time you cannot ensure that it's in equilibrium, right? While it's moving, then there is also change in state. Okay, that time you cannot ensure, but before and after you can ensure 1 milligram, 1 milligram you are removing, moving means a small states undergone by the system are all equilibrium states. So that kind of process is called quasi-static process, just like a reversible process, but not exactly reversible process, because it's not at all possible to have a reversible process, because while it is moving at that time, the pressure, there is a pressure difference between inside and outside. If there is a pressure difference, you cannot call it an equilibrium state. So that state is not an equilibrium state, but before and after is in equilibrium state. So most of the states are equilibrium state, but not all the states are equilibrium states. Therefore, any reversible process is not possible. What we can do is I have a quasi-static process in which most of the states undergone by the system are equilibrium states. Okay. This is an example of quasi-static process. Okay. Note it down and then we go to the next topic. Okay. I explained you quasi-static process. Okay. What is quasi-static process? As good as reversible process. Okay. Approximation of reversible process is quasi-static process. Okay. Note it and raise your hand, please. This example alone, you note it down and raise your hand. Noted, everyone? Ellen, noted? Okay, clear? Now we will talk about heat engine. Now we are going to talk very important topic, most important topic in the chapter, heat engine. Heat engine is a device is a device, note it down, which converts heat energy into mechanical energy. Heat energy into mechanical energy. Before this stating about heat engine, I want to talk about cyclic process, very important. Before that, we just discussed the cyclic process. Cyclic process is a combination of various process, maybe process 1 to 2, maybe like means several other processes involved, but initial state and final state will be same. Maybe you are going like this first process, then you go like this second process, then you go like this third process, and then you go like this fourth process, 1 to 2, 2 to 3, 3 to 4, 4 to 1. So this kind of reversible thing means sorry, cyclic thing, you started from one and ending at one. That means the starting state and ending state are same. Okay, initial state and final state are same. Initial state and final state, we call it a state, right, are same. That kind of process is called cyclic process. It is composed of minimum two number of process, minimum two, 1 to 2, and suppose it is 2 to 1 means 2 to 1, like that. So two processes are involved, and more than two processes are also involved, 1 to 2, 2 to 3, 3 to 4, 4 to 1, like that. Also 3 also can be there, 1 to 2, 2 to 3, 3 to 1, like that also it can be there. So the minimum of two process in which the initial and final states are same, that is called cyclic process. Okay, can you note it down? What is cyclic process? Minimum of two number of process in which initial and final state are same are called cyclic process. Okay, please note it down. Then we'll discuss the heat engine. Okay, noted. Can you raise your hand if you noted? Ah, Ellen, Mahalakshmi, Nishant, Harini completed, na? Okay, so now coming to see, I want to explain you that what you call that Carnot cycle. Okay, before discussing this heat engine, I want to explain you Carnot cycle. Carnot cycle is nothing but it is composed of four process. It's a cyclic process, reversible cyclic process. All the processes are reversible in nature. First is isothermal expansion. Second is adiabatic expansion. Third is isothermal compression. And fourth is adiabatic compression. Please note it down. Then I will explain you one by one, step by step, how this Carnot cycle works out. Okay, Carnot cycle consists of four reversible processes. Carnot cycle represents four. It consists of four reversible processes in this order: isothermal expansion first, then adiabatic expansion, then isothermal compression and adiabatic compression. Okay, note it down and raise your hand, please. There are four processes involved in Carnot cycle: isothermal expansion, then adiabatic expansion, then isothermal compression and adiabatic compression. Four processes are involved. Note it down. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Note it down, please, and raise your hand. Carnot cycle, very very important cycle, consists of four reversible process: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Okay. Mahalakshmi, Nishant, noted. And one more thing I want to tell you that so what is this kind of first of all I want to just explain you how you can achieve an isothermal expansion means just I want to relate with you understand that what is how isothermal expansion will happen. That means this is a piston cylinder arrangement. This is a cylinder and piston arrangement. Okay, cylinder and piston, whatever you call it, and inside that gas is there. Mostly in thermodynamics we talk about gas. Okay, it's a compressible gas, and you have to do the isothermal expansion means first of all you should understand that the main thing is temperature should be constant in this process, right? So that means whatever heat you are supplying, that will should be converted into work without increasing the temperature of the gas, without increasing the temperature of the gas. Whatever the heat you are giving, you have to convert into work. That is how somehow you have to achieve it. Okay, it's a imaginary type of thing, very difficult to achieve like that. Okay, but it's a that is only called as isothermal expansion. Isothermal expansion, I think it's very slow process. You have to do it very slowly. Okay, and it has to be reversible in nature. We are talking about reversible process. So step by step you have to do it, and somehow you have to supply the heat and expansion will happen, and you have to ensure that the temperature of the gas should not increase. Okay, how you are going to ensure that and all is there. Okay, that and all is there, but that is how isothermal expansion works out. Okay, understand what is isothermal expansion? You have to supply the heat, it should get converted into work, and no, there should not be any increase in temperature of the gas. Whatever heat you are supplying should not increase the temperature of the gas, should not increase the vibration of the gas. It should only make the gas to expand. Okay, clear? Note it down, raise your hand after noting it. We are talking about reversible isothermal expansion. Okay, reversible isothermal expansion. Okay, reversible isothermal expansion. Give the heading reversible isothermal expansion and note down this explanation. Then raise your hand after that. Okay, reversible isothermal expansion. Noted, noted. Ellen, Harini, Mahalakshmi, Nishan, noted. Okay, now coming to reversible adiabatic expansion. That means you should not allow any heat transfer to happen. You have to insulate it. Okay, some insulation you have to apply so that there is no heat transfer between the gas and the surrounding system and surrounding. This is a system, and there should not be any heat transfer. Heat transfer should be zero because it's adiabatic process, and only there will be expansion, and that gas will expand. Maybe outside pressure is less than the inside pressure. Gas will expand, and there will be change in volume, and but this will happen adiabatically. Okay, so this is called reversible adiabatic expansion. Okay, clear? And whatever the work done by the gas will be equal to the change in the internal energy, right? And next one is reversible isothermal compression, similar to that what I explained you. And next is the reversible adiabatic compression. Okay, all these things are there. Okay, now clear? Now we'll come to, so now we will come to our Carnot cycle. Carnot cycle involves these four processes and how to represent them on a PV diagram. Always remember that slope of the adiabatic process will be more than the slope of isothermal process. If isothermal process is like this, adiabatic process will have somewhat more slope. This is the process 1 to 2 isothermal expansion, in which volume will increase and pressure will decrease, and it will follow the equation PV equal to constant. 2 to 3 is the adiabatic expansion, PV power gamma is constant. 3 to 4 is again isothermal process. Okay, actually speaking, I have written some, I think a small mistake I have done. I should have told you like this: isothermal heat addition. Isothermal heat addition. Okay. Second, adiabatic expansion. Same thing only, but it is written this manner. Okay. Isothermal heat rejection. Heat rejection. Fourth, adiabatic compression. Like that we generally write. Okay. Compression. So please correct that. Isothermal heat addition, adiabatic expansion, isothermal heat rejection, adiabatic compression. So this is again PV equal to constant. In this process, heat is added to the gas. Okay. In this process, work is done by the gas. Okay. And in this process, heat is rejected by the gas to the surrounding. And in the process 4 to 1, that is the heat is again uh, work is done on the gas. Okay, work is done on the gas. So in the process 1 to 2, heat is added isothermally. In process 2 to 3, work is done by the gas adiabatically. In process 3 to 4, heat is rejected by the gas isothermally. In process 4 to 1, work is done on the gas adiabatically. Okay, so I will write down here properly. If you want to note it properly, note it down. I'll write all the four process and what is happening in each process. This is the diagram, already I have drawn it. This is a Carnot cycle. Okay, so what we are doing in the Carnot cycle is I am writing all the processes which are happening in Carnot cycle. Process 1 to 2, heat is added. Heat is added to the system. System means gas. Added to the system isothermally. That means keeping the temperature constant, you are adding the heat. Okay. Process 2 to 3, work is done by the gas. That means gas is expanding. Work done by the system. By the system means expansion process. Okay. That is adiabatically. Adiabatically. Okay. And then next is 3 to 4. That is 3 to 4. That is heat is rejected by the system to the surrounding. Rejected by the system to the surrounding in isothermal manner. Isothermally, that means keeping the temperature constant. Okay. And 4 to 1 is work is done on the gas. That means we are compressing the gas. Work done on the gas. Work done on the gas. Okay. On the gas adiabatically. Adiabatically, that means you are doing the compression process but in adiabatic manner. Okay. Adiabatic manner means heat transfer is zero at that time. Okay. Clear or not clear? All the four process, note it down. To properly note it. Okay. This thing nobody will tell you. Nobody will explain you this simple manner. Okay. And this much, if you write in exam, 100 marks you will get. Full marks you will get. They will not cut any marks for you. Okay. So write in the same manner the way I am telling you. Okay. Write it and raise your hand. Okay. After that, these are the four process, reversible process involved in an Carnot cycle. Okay. Clear? Mahalakshmi has noted. Others also note it and tell me. Pelen, Nishant, Ellen noted. Okay. So who will repeat this thing? I will ask one by one process from each of one of you. So Mahalakshmi, you tell what is the first process, 1 to 2 process. Tell. Don't write in chat box. You tell. Unmute and tell one by one. What is process 1 to 2? Tell me one by one.
Heat is added to system isothermally.
Heat is added to the system isothermally. What is isothermally means? Do you know what is the meaning of isothermal heat addition? That means temperature
The
is what?
temperature remains constant.
Temperature will remain constant. When you give heat, normally when you give heat in routine life, when you heat something means definitely temperature will increase. And maybe it will expand also. Like in a balloon, air is there and you are heating that balloon, then balloon may expand because air is expanding, but at the same time balloon will get heated up also. But here when this we talk about isothermal heat addition means you have to do the process in such a manner that whatever heat you are giving that will only cause expansion. It won't cause any temperature increase of the gas. Okay, that is called isothermal heat addition. Special way of adding the heat. They are not normal adding heat. This is a special manner in which you are adding the heat. A controlled process. Then what is 2 to 3? 2 to 3. Harini, tell me what is 2 to 3 process? State 2 to state 3.
PV is constant, sir.
No, no, no. State 2 to 3 I am telling. First 1 to 2 PV is constant. That is isothermal process. What about 2 to 3 process? Second process. Second process. First process is over. Mahalakshmi told. First process isothermal heat addition. What is this process?
The system expansion. The work done by
Just a minute. I'm getting a call. Wait a minute. Tell me what is the process 2 to 3?
the work done the system it expands. So
Gas is expanding, but in such a manner that there is no heat transfer to the surrounding. During expansion, the heat transfer is stopped to the surrounding. Somehow you are insulating the system in such a manner that we are not allowing any heat transfer to happen between even though the system may be at higher temperature or lower temperature, but we are not allowing heat transfer to happen between system and surrounding. We are allowing the system to expand. If it wants, it can expand. So we are that expansion is happening, but without any heat transfer. That is called adiabatic expansion. Okay. What is that called? Adiabatic.
adiabatic expansion.
Adiabatic expansion means there is expansion, but heat transfer is zero.
Yes, sir.
Equation, which equation it will follow? P into V power gamma is constant in this process. Okay. Adiabatic process. Now you tell here, Nishant, what is the process 3 to 4? Nishant, what is process 3 to 4? You are not audible, Nishant. Some network problem or what? Unmute and again tell. Everyone can hear me. Others can hear me. Oh, Nishant, but you are not audible. Again, try please.
Can you hear me, sir?
Yes, I can hear you.
Uh, there's no heat transfer, sir, so it's close.
No, yaar, there is a heat rejection in 3 to 4 process. We are doing it isothermally. We are keeping the temperature same, but still we are able to reject the heat. 3 to 4 is a heat rejection process. Isothermal heat rejection process means we are doing heat transfer but isothermally. We are keeping temperature same in process 3. Understanding?
Yes, sir.
Hmm. What is the equation which will be followed? PV equal to constant. Again, I will ask one more time. Now you have understood now. Next time again I will ask. Now tell me another. Ellen, you tell what is the process 4 to 1.
Sir, the work is done by the gas adiabatically.
Work is not done by the gas. Work is done on the gas.
Oh,
Again,
sorry, the work is done on the gas.
on the gas.
No
We
heat
are
transfer takes place.
no heat transfer, compression work. We are
Yes,
compressing the.
sir.
Okay.
Yeah.
So again, I will ask one by one. All of you have written this, na? All the four. So again, I will ask you one by one, and you have to tell properly. Now again, Mahalakshmi, you tell. What is the process 1 to 2?
The heat is added to the system without change in temperature.
Or you can say in simple other word, technical language, isothermal heat addition. That means without change in temperature, heat is added to the gas. Okay. Which equation will be followed in the process 1 to 2?
PV is equal to C,
PV is equal to what?
constant.
Constant. What is P? What is P and what is V? I am only teaching myself or what here? Because I think that basic things itself I not be able to make clear to you. What is P and what is V, Mahalakshmi, you know?
Pressure and volume of gas, sir.
Pressure of the gas and volume of the gas. Okay. How you can find the volume of the gas? Is it possible to calculate the volume? Because generally gas will spread, na? How you will calculate its volume? Whether it is volume of one molecule of gas or some collection of gas or what it is actually. Whatever is your understanding, you share so that I can also contribute to you.
There is a molar number of moles we can
No,
calculate, sir.
no, sister. What I am telling is, you understand what is this V is representing here. Actually, the system which you are telling system again and again, it is a gas confined in a piston cylinder arrangement. Basically, it is like that. Normally, it's like that. It's a closed system. Whatever we are doing now today, it's all about closed system. There are two types of system, three types. I told you initially yesterday's class: closed system, open system, isolated system. Closed system is that system which allows heat transfer and work transfer, but does not allow mass transfer. That means the system is closed. That lid is closed. Maybe that system can expand, but the amount of the gas is confined in a space, like inside a balloon or inside a piston cylinder, but piston can expand. So this type of system we are talking there, okay? And in that, whatever the volume in which the gas is occupying the space, that volume we are talking actually. There are so many lakhs and lakhs of molecules in that confined system. How much volume it's occupying, that volume we are talking about, okay? If it will expand means that volume will increase. If it compresses means volume will decrease. That's all. But it has some boundary. There is a boundary between system and surrounding. What is system? Whatever we are studying, that is system. We are studying the gas. The gas we have considered as a system. Okay. System may expand, system may compress, system may get heated up, system may get cooled down. Okay. These four things can happen to the system. And second is pressure. Pressure is nothing but whatever, now since there are gas, no, they are vibrating all the time. And they will even strike the container in which they are kept. And whatever the force they will apply on the container, average force, and divided by the area of the container, that is the pressure. Okay. Pressure is nothing but like a force only. The force applied by those molecules of the gas on the surroundings. That is the pressure which we are talking about. Okay. Understand? And you know that the gas which is inside the cylinder, outside the cylinder, there is a atmospheric pressure. That means the air is pressing that piston, and inside it's a gas. So gas is also pressing the piston. Both are pressing it. So the one which is pressing it more, the piston will move in that direction. Okay, understand? You played with a syringe or not at home? That syringe which is used in hospital. That what you call it? You have played with it, right? All of you must have played with that plastic syringe in which your piston cylinder, you might have seen that, a rubber thing and inside it. Yes or no? That most of you might have played with it. Okay. So that is also the example of piston cylinder arrangement. Okay. But that is an open system because water is allowed to go out of it. Okay. So this is pressure, this is volume which we are talking. Okay. And PV equal to constant means the multiplication of pressure and volume is constant, means if volume will increase, pressure will decrease. If you increase the pressure, volume will decrease. Okay. Now tell me, Harini, you tell what is the process 2 to 3?
So the work done by system expands with no heat. So the heat here is 0. And the equation is pressure volume gamma is equal to constant.
Okay, don't get panic. I just want you to understand that only. My intention is that what is that heat is 0 means what do you mean by that?
So even without heat, it expands the.
System will expand even without transfer of heat.
Yes, sir.
If it expands, its temperature will reduce or its temperature will increase.
Oh.
No, you think and just normally tell, no need to see anywhere and all. Suppose you are not giving any heat. Normally you think, see, we are talking about energy interaction with the systems. Energy interaction within a system means, suppose you think like that, I give you a balloon. Okay, inside that I feel air inside it and I give it to you. Okay. And I will tell that the balloon is expanding automatically. Okay, expanding automatically without you are not heating anything. That means from where is getting that energy? For expansion, it needs some energy, right? But you are not giving any energy, you are not heating it also, but it's still expanding. So from where it will get the energy? It will get the energy from its own internal energy. Internal energy means it is in the form of temperature. You know, the temperature will reduce and it will expand and it will basically it cools down. Okay, while expansion, because you are not giving any outside heat to it. Okay, understanding?
Yes, sir.
If you understanding, then you explain me process 4 to 1, not 3 to 4, 4 to 1. What is 4 to 1 process? Just reverse of it.
It expands with heat.
4 to 1, it is not expanding, it is compressing. You can see also V4 is more than V1. Horizontally you see 4 is ahead of 1. So volume of 4 is more than volume of 1. That means it's compressing. 4 to 1. Whether heat transfer is taking place in 4 to 1 process?
Yes, sir.
No, not taking place now. It's adiabatic process. 2 to 3 and 4 to 1 both are adiabatic process. 1 to 2 and 3 to 4, these two are isothermal process. 2 isothermal, 2 adiabatic. Okay. In 1 to 2, you are adding the heat isothermally. 2 to 3, the system expands adiabatically. 3 to 4, you are rejecting the heat isothermally. 4 to 1, system is being compressed adiabatically. Like that, you have to remember. Okay. 4 processes are involved. 1 to 2, isothermal. 2 to 3, adiabatic. 3 to 4, again isothermal. 4 to 1, again adiabatic. 1 to 2, temperature is constant. 2 to 3, heat transfer is 0. 3 to 4, again temperature is constant. 4 to 1, heat transfer is 0. 1 to 2 is expansion. 2 to 3, compression. Sorry, 2 to 3 also expansion. 3 to 4, compression. 4 to 1 also compression. Okay. So how you have to remember? 1 to 2, isothermal heat addition. 2 to 3, adiabatic expansion. 3 to 4, isothermal heat rejection. 4 to 1, adiabatic compression. Like that you have to remember. Okay. Now you tell me, Nishant, you tell, what is process 3 to 4?
Isothermal compression, sir.
Compression, you can say isothermal heat rejection is a better word. Okay.
Yes, sir.
Because it is making clear that we are rejecting the heat anyway. So what is process 4 to 1, Ellen?
So work is done on the gas adiabatically. So it's compression and no heat transfer takes place.
Heat transfer takes place. Okay. Okay. So yeah, please, if you want, means one time you just do one thing without seeing anywhere. You write what is 1 to 2, 2 to 3, 3 to 4, and 4 to 1 in your copy. Write it one time. Okay. I will tell, and then you write without seeing anywhere. 1 to 2. One time you listen to me and try to write it in your copy. Okay. Or you can make a chart. This you have already written. Now you make a chart like this. I will tell you how to do, how to write like this. You make a chart, and 1 to 2, 2 to 3, 3 to 4, 4 to 1. Then you write here first whether it is isothermal, and this is adiabatic, this is isothermal, this is adiabatic. Then here you write heat addition, here you write expansion, here you write heat rejection, then you write compression. Okay. Then what is the, here you write temperature is constant, here you write heat transfer is 0, again temperature is constant, heat transfer is 0. Okay. Like that you have to remember. Okay. And equation PV equal to constant, here PV power gamma is constant, here PV equal to again constant, here PV power gamma is constant. Okay. Like that you can remember. Okay. And the graph also you have to remember. 1 to 2, then 2 to 3, 3 to 4, and 4 to 1. You should represent like this: Q add, Q reject. Work done by the system, work done on the system. Okay. In fact, remember, Q1 to 2 is positive. I will tell you. Okay. Q1 to 2 is positive. W2 to 3 is also positive because it is done by the system. But Q3 to 4 is negative work, negative heat, because it is rejected by the system. And W4 to 1 is also negative because work done on the system is negative. Yesterday I taught you. Work done by the system is positive, work done on the system is negative. That means expansion work is always positive and compression work is always negative. Heat given to the system is always positive, heat rejected by the system is always negative. Please write down all these things. Okay. Note down this page, whatever I written here. Then I'll ask you some questions. You are be ready to answer. Okay. Note it down, please. Note it and raise your hand. Noted. No, don't get disheartened and all. Okay. Because slowly you will understand here. I am teaching from so many years. I am telling like that, but it's not easy actually. Okay. But I trying to explain you. That's all. Okay. But it's simple only. First thing you remember that it's a closed system. Okay. Note it here. Note it. Then I will explain you once more. Noted, Ellen? Noted? See, I just tell you one thing. You should know the characteristics of each process, okay? 1 to 2. In 1 to 2, what is happening, I'll tell you, okay? I'll tell you one by one. In 1 to 2, you are adding the heat isothermally. That means your temperature T1 is equal to T2 actually, okay? But P1 V1 equals to P2 V2. Okay, and you can write the first law of thermodynamics also. Q1 to 2 is W1 to 2. Change in internal energy will be 0 because it's isothermal heat addition. Okay. Even though you are adding heat, temperature is not increasing. Whatever heat you are doing, adding, that is causing the expansion. Okay. That is causing, but we are not talking about expansion process, but expansion is happening. That's why the graph looks like this. V2 is very clear, that pressure volume graph, you are very clear that P2 is less than P1 and V2 is more than V1. That is very clear from the graph. Okay. So it's an expansion process only, but we call it as a heat addition process. Okay. Just namesake. Okay. So heat is being added, and that adding heat is being added isothermally, and whatever heat is getting added, that is converting into work, that is causing the expansion. That's all. Because there is no temperature increase, temperature is constant. Okay. Are you getting it? Just always you people are raising hand when I'm asking the question. Now people are silent. So only I'm asking again. You please note it down if you have any doubt. Okay. You understand here. Whenever you give heat to somebody now, suppose I heat you. Okay. I put a lighter and he start heating you. Okay. Two things will happen. Always remember. Okay. Two things will happen. Your temperature of the body may increase. And second thing, you will expand. Okay. You can imagine it. I am heating you with a candle. Two things will happen to you, possible to happen to you. First, your temperature of the body will increase and you will expand. Okay. But in isothermal heat addition process, temperature is not allowed to increase. It's a controlled process. If temperature is not allowed to increase, whatever heat I am giving you, suppose 100 joule heat I have given you, 100 joule of work will be done and you will expand. Totally 100 joule will contribute to the expansion process, will not allow any temperature increase. Okay. Understand the meaning of isothermal heat addition. Okay. This ISO, you note it down, note it and raise your hand. Okay. 1 to 2 process. Clear now? Process 1 to 2. Graph is also clear now. Note it and raise your hand. Okay. 1 to 2 process. Okay. Now I'll tell you about process 2 to 3. Okay. Process 2 to 3 is adiabatic expansion. That means you are not going to do anything. System will expand automatically. Heat transfer you will not allow to happen. You will insulate the surrounding so that heat transfer is not happening. Then whatever heat transfer is, you are writing this equation. Now heat transfer is not there. Whatever work is being done is done being the expense of internal energy. Okay. That it means it will cause cooling, automatic cooling of the system. That means temperature will decrease. Temperature will decrease. Okay. Heat transfer will not happen, but temperature will decrease without heat transfer also, because the system is doing work on itself. Okay. So heat transfer will not be there. Temperature will decrease. And again, this process P2 V2 power gamma is equal to P3 V3 power gamma will be followed. And again, pressure will reduce, and this is the process 2 to 3. Expansion is happening. V3 is more than V2. P3 is less than P2. Okay, PV power gamma equal to constant is being followed. Okay, this is the adiabatic expansion process, 2 to 3 process. Okay, clear? Note it down and raise your hand. 2 to 3 process. Noted. Noted, Nishant. Then here process 3 to 4. 3 to 4 is 1 to 2, 2 to 3. Then 3 to 4 is isothermal heat rejection. Temperature is constant. T3 equals to T4. Heat rejection is allowed. Whatever heat rejection that will be equal to work, because change in internal energy will be 0 because temperature is constant. Okay. And that's all. Okay. Volume will decrease. V4 is less than V3. Pressure will increase. Graph will be followed. P3 V3 is equals to P4 V4. Isothermal. Like this. 3 to 4. You can see that pressure is increasing and volume is decreasing. V4 you can see less than V3 and P4 is greater than P3. Okay. This is 3 to 4 isothermal heat rejection. Okay. If you are written, raise your hand. Harini, Mahalakshmi, Nishan, note it down. Okay, the last process is adiabatic compression. Okay, adiabatic compression. Heat transfer in 4 to 1 process is 0. Change in internal energy, na, E1 minus E4. Okay. Okay, this is the equation. These are the equations. Okay. Note it down this also. Okay. Tomorrow morning you are there, Ellen. You are available tomorrow morning, Ellen. Huh? You are available, na? Okay. Tomorrow morning, na 6 o'clock we have our class. Okay. Morning 6 o'clock we'll have class 6 to 8. Remaining portion of the chapter and next chapter. Remaining portion of chapter and questions we'll do tomorrow morning. Meanwhile, you please revise everything. Whatever I taught, please revise it thoroughly. Please revise it. Okay. This class recording also I will send you. Please revise everything. Okay, now work done, formula, all those things you revise it. Okay. Okay, then bye. Okay. Morning 6 o'clock, please attend the class. Same ID.